By pulling the string, which was connected to the side, you're able to get this thing to spin. Sound like what you did in the lab? Okay. You videoed the tape coming off. And from that moment, the only thing acting on the T was friction. Friction was a torque that slowed down the spin of the T. You counted the number of rotations it made as it was slowing down. And using the video, you should have been able to time how long it took for the thing to make it from whatever initial velocity it had to a final velocity of 0. So this is probably in seconds. You'll need to convert this to radians, because what I want you to calculate is acceleration. You'll need a motion equation to do this. I'm sure you can figure out which one, but I say those kinds of things and then people go, I don't know what I'm supposed to do with this. No, that's because you don't pay attention in class. This will probably do it. Now, you should have a bunch of data, like 7 to 10 of these that you pulled at different speeds. So if it were me, I would probably use a computer to do this. So you could put your raw data in it and have it just calculate the acceleration for all of it. If you have difficulty using a computer to do this, I would be happy to help you with your spreadsheet. Just share your spreadsheet with me and give me editing privileges, and I'll help you with what it is. Put the data in there and try. You're going to use this to generate a formula and put that formula here. Anna? Again, you don't have to. If you want to do it all by hand, that's fine. But I'm about to tell you what I want you to do for the lab, but what's going to be different here is I'm also going to be teaching you a new concept. So this is the data as you have it laid out. Here's the concept. We have, from first semester, the idea of net force causing acceleration. This is a first semester topic. We know from Newton's second law that if the force is unbalanced, then the object accelerates. But, and this part's important, forces on their own do work. If the force was unbalanced, then net work was usually done. A certain amount of energy that was given to the object to cause a change in kinetic energy. Right? This would have been something like force times distance, or the net force times distance. And it would equal 1/2 mv final minus 1/2 mv squared initial. This was the foundation, was Newton's second law, but it created the concept of work and energy. And we then also talked about potential energy from this. All right, this was a first semester topic. Second semester, we also talked about the fact that if there's an unbalanced force over a given time, that this would change the momentum of the object. We called this impulse. And we defined momentum as mass times velocity. An unbalanced force causes an impulse. It causes a change in momentum. So we started with Newton's second law, and we did Newton's second law problems, which, there was lots of different kinds. There was the ones that you tended to hate the most in the beginning, but towards the end, most of you got pretty good at doing these. Like, does this look familiar? Right? Atwood machine style questions where you had to figure out the acceleration of the system. And we also had problems that looked something like this, the box sliding down the ramp kind of problems. That all look familiar to you guys? These were kind of the net force problems that we had. Well, causes a change in an object's motion. and that change in motion can cause a change in energy or momentum, then there's going to be an analogy here. If net force and net torque is going to have something similar. We already dealt with static problems in which net torque was 0. I use that to help you figure out how to deal with the fact that a torque is more complicated than a force, that a torque requires that you assemble information about how to apply that force to cause a change in rotation. Today, I'm going to add to that conversation for situations in which the net torque isn't 0. We already talked about the fact that objects that rotate have a more complicated relationship with their inertia, that the shape of the object determines how it behaves. And we dubbed that the moment of inertia. So obviously, inertia is going to play the same kind of role as it does for mass. In Newton's second law, the inertia was just the mass of the object. For second law for rotation, the moment of inertia is the inertia of the object. So if you apply an unbalanced torque, you're going to change the object's rotational motion. You're going to cause it to accelerate. How much acceleration you get depends on the inertia of the object. It's still just Newton's second law. But this is Newton's second law for objects that are spinning. So if you want to get something to rotate, you have to apply an unbalanced torque. How much that thing will rotate will depend on its moment of inertia. The result will be some form of acceleration. Now you should anticipate that we're going to develop not only Newton's second law here, but we'll have problems that are going to be similar to the problems we had first semester, but now the things that are spinning in our problem suddenly have inertia that we didn't consider before. So the problem that we had just a minute ago with the box. You have a box on the table, and a box hanging off the table. We never cared about the pulley. In fact, first semester we would just say the pulley is massless. Well, that's not the case anymore. Our pulleys have inertia, and therefore, because they have inertia, they affect the system. So this problem comes back to us, but now the pulley plays a role. The pulley's involved. In fact, we'll have problems that are just the pulley. This is the demonstration we did yesterday, day before yesterday. The one where I was playing with the stuff that spun. On that date, if you'll remember, it's sideways, but we had a weight fall while an object spun. So this would fall, and this will spin. If this object has inertia, then it doesn't just fall straight downwards. The block is going to have to apply a torque to the thing that's spinning. And the thing that's spinning has inertia. It wants to resist the changes in its motion. So we'll have unbalanced torque problems that are going to require us to look at the net torque of the system and decide how it accelerates. And I don't think this is a big stretch, but you can probably imagine that we're also going to have these guys come back. But now we have stuff that can roll. And its inertia is going to play a role in how it makes it to the bottom of the ramp. It's still the box problem with mg sine thetas and stuff like that, but now the object rolls, and friction does things differently when things roll than when things slide. So these problems all come back, but they come back now with inertia involved a little differently than before. And I don't want to look too far in the future, but you can probably imagine that there's going to be rotational work and rotational energy. If an object has inertia and you if you apply torque to it to get it to turn, once it's spinning, there's something different about it. That object is moving, and that motion must translate into energy. And I think it's probably not too much to consider that there'll be angular momentum. Once something's spinning, it stays spinning. But here's something that's different, and this appeals to at least one of you in the room. Once you start spinning, you have angular momentum, just like once you start moving, you have linear momentum. When something had linear momentum, generally, it changing shape didn't affect its momentum. It would just have a different shape because the mass didn't change. But if something's spinning, its shape could change while it's spinning. We know shape affects inertia. So when an ice skater spins and they have their arms flung wide, their moment of inertia is large, right? Because they're spreading their mass out. And when they pull their arms in, they change their moment of inertia. Well, momentum is a conservation property. Right? Conservation of momentum. So if they start with one momentum, but change their moment of inertia, they can change how they spin. That's what ice skaters are doing. That's what ballet dancers are doing. That's what anybody who is changing their shape and spinning is attempting to manipulate. So almost all the moves that you tend to see ice skaters do are about manipulating their moment of inertia. They would never say those words because that's not how they're trained, but that's what they're doing. That's the entire thing. Every pose, every one of them is about manipulating how far away from the axis of rotation their body parts are. So when you look at dancers, one of the things they're almost always rated on, because it's competition season right now, and they're all going to Lakeland to compete, or Orlando, or some silly high school around town, and they're all going to be there that weekend, and they're going to have all these great stories on Instagram about how they spent the night there doing their homework together, blah, blah, blah. They're all going to be super hypercritical of themselves when they see videos of themselves and they're not perfectly upright during their spin, because that's how they're rated. And they know that being perfectly upright is a rating thing, but it's also better and easier for them to manipulate their body under those circumstances. That's why they're rated that way, because the person who's rating them understands that performing like that requires precision, because the precision plays into these factors. So, although I know that you tend to think it's just physics and it's dumb, but it really does have reach in ways that you don't fully appreciate until you're the one that's being judged. And they say, well, you weren't perfectly upright. And because you weren't perfectly upright, you weren't perpendicular to the ground, you had these problems. Well, the person who trained you told you that and said, this is why you want to be in this position, because it does things for you as a dancer, as a skater. All right, enough of that. Let's get back to what you need to do. Your lab is relatively straightforward. So let me come back to that for the time being. We can't calculate this portion of the torque because in your lab, the friction was inside. It was between the pole and the tube. So there's no way to measure that frictional force. However, you determined this theoretically. Right? You determined I theoretically. It's still on the board over there. So you have a calculation for I. And alpha, you're determining experimentally. Right? You collected data, delta theta and time and final velocity 0. So I want you to tell me what the average frictional force was by finding the individual frictions that occurred, average frictional torque, by finding all of the accelerations. So for each acceleration, I want you to calculate the frictional torque. It'll be the product of the moment of inertia. You calculated that theoretically. So this is the moment of inertia of the system, the T, times each one of your accelerations. I'll put a little n there because you probably have 6 or 7 of these. That will give you the frictional torque. I want the average frictional torque that acts on the T. Everybody should be about the same because the frictional torque works the same way for each of the apparatus. So although you won't all get the same number, you should all have the same order of magnitude here. And this is a pretty big frictional torque. It slowed your thing down in just a couple of seconds in most cases. So it was actively trying to slow it down. Unlike that one, which has very low frictional torque, your apparatus had a pretty high frictional torque. This number should end up being the same for all of your trials, but you'll find out it's not. And there's a good reason for it, and I'm going to ask you to come up with a theory as to why the frictional torque seems to be higher on the ones where it was spinning faster. Your data you should know which ones are the ones where it's spinning faster because the value for T and delta theta will be bigger, right? You spun it faster, so it took longer to come to rest. You're probably going to find that those frictional torques are greater. And I'll give you a hint. It's not friction. It's something else. Something else happens when it's spinning faster than when it's spinning slower. And so think about that and answer that question at the end of your lab. Why does it appear that there's a stronger frictional torque when it's spinning faster than when it's spinning slower? Of course, if your data doesn't show that, then you don't have to answer that question. We're going to look at real problems now. When I say real, I mean problems that involve both net force and net torque. You have a series of steps to solve force problems, a set of steps that you wrote down first semester. Solving problems that involve torque and force are the same. They still have the same series of steps. However, because torque is involved, there's a few more things you have to do. So what I want to do is kind of review the set of steps that you already have. And I'm going to write those down as we go, but I'm going to apply them to this problem. Can you imagine what would happen in the system that I've just drawn? If I had a big pulley like this and I wrapped a string around it a bunch of times and then hung a weight off the side, can we all kind of agree that had we set this problem up, this box is probably going to fall downwards while this pulley turns this way? Like we release it from rest, and there is an acceleration of this box downwards and an acceleration of this pulley in the clockwise direction. Is that reasonable? This is kind of the thing I had set up over there. As the box fell, the thing spun. You guys recall that? And it's still set up, so you can play with it. I'd encourage you to do so. There's differences here. In the one that we had in the classroom, I connected the string to the spindle because I couldn't connect it to the outside of the big disc thing. So I connected the string to the spindle instead. So I had a smaller radius that it was acting on. I'm going to just draw this problem with it acting right on the outside edge of the pulley. Is that okay? I've taken the thing that's spinning and I've turned it sideways so it's spinning this way. All good? All right. So in a real Newton's law problem, you have to ask, is it a first law or second law? We decide that at the very beginning, right? So this is going to be a second law problem. Our system's going to accelerate. So we make that decision first, though. First or second law? The next thing we do is identify each object that's moving. I mean, that's what we did before. What are the objects in our problem? And when you're identifying them, one of the questions you have to ask, does the object have translational motion? Because then it's net force. If it's rotational, then it's net torque. And of course, it's possible to have both, where you have to apply net force and net torque. So something that's rolling, that would have both. Now, when we look at our Atwood machine question here on the side, is it clear to you that one of these objects has translational motion and one of these objects has rotational motion? So in this case, I'm going to apply net force to the box that's falling and net torque to the pulley that's spinning. There are lots of forces acting on the pulley, but I only care about the ones that are causing a change in rotation. And there are forces acting on the box, none of them are changing its rotation. So, let's talk about the net force part. We know how that part behaves, right? You go through and ask yourself, what are the forces acting on the object? Same group of forces we've had before: weight, normal forces, tension forces, friction. We go through the list, right? Draw a free body diagram that indicates each force as it acts on the object. So same thing, we're gonna do that over here. We're gonna take and look at the box. The box has a group of forces acting on it. So can we agree 2 forces acting on the box? What's one of them? All right, tension. What's another one? I'm gonna be intentional about my diagram too. I think the weight's greater than the tension, which is why the system accelerates downwards. In fact, I have to go one step further. If you recall, you also have to decide what is the direction you're going to call positive. And I would suggest that we make the direction of the implied motion the positive direction. So I apply Newton's second law. I add up all the forces and set them equal to ma. Right? A net force problem. So here we'll have mg minus tension equals ma. So here's where we have a little bit of a difference. We have a net torque problem. So in the net torque problem, there's more things to do. We still have to identify forces. We also have to identify the pivot. And when we identify forces, where they act becomes important. Right? We're suddenly having to keep in mind, not just that they all act on the object, but some of them act maybe at the pivot, and some of them act away from the pivot. So let's consider the forces acting on the pulley. The pulley's got weight, right? But the weight acts at the middle. The spindle thing that's holding the pulley, it's pulling up. Those are 2 forces that act on the pulley. But where do we think the pivot is for the pulley? So we all think it's right there at the center, right? The pivot's right here. So do either of these 2 forces cause a torque? No, the torque arm length is 0. But there is a force that is causing a torque, right? The tension acts on the pulley too. Now the tension doesn't act at the pivot, so the tension is causing a torque. So we have drawn in all the forces, taking into account where they act. I'm also going to decide a direction that I call positive, and here's where you have to be really careful. I want to select positive to be similar to the positive I selected for the box. So I think the pulley's going to rotate in the clockwise manner as drawn. That's linked up with the positive direction of the box. Right? If it goes clockwise, the box goes down. Now, unlike force, we have to assemble the torque calculation. Right? R times F times the sine of the angle. That's assembling your torque calculation. You have to do that for each force that is causing a torque. So for us, assembling that's pretty easy. I have to figure out where the force is being applied, and it's being applied a distance r away from the pivot point, right? The radius of the pulley. So I'm going to use a capital R for that. So my torque arm is R. The force that's causing this torque is the tension, so I'll use the capital T that we're using for tension. This tension here is the same as the tension over here, right? The tension in the force equation is the tension that's causing the torque. Now, I have to do that for every single force that's acting, but I also have to qualify the angle. For all pulleys that are round, the string always comes off a pulley at a tangent. So for every pulley, it's always going to be sine 90 degrees. You add up all the torques, you take into account their direction, and you set that equal to I alpha. So net torque equals I alpha. But there's a 5 here. More steps for torque, because you had to assemble the torque, but you also have to consider the shape. And find the moment of inertia. Just give me one more sec. Would you guys agree the pulley's probably a disc? So you look up on the chart, 1/2 mr squared. That's our disc. Now, we didn't finish, but there's one thing I need you to write down. You have to ask yourself at this point, is the acceleration of your box connected to the acceleration of your pulley? Does the rotation of the pulley connect with the acceleration of the box? Does one rotation of your pulley mean your box moves one circumference? If it does, you can use this relationship to link these two things together. That's how you solve these problems. So the last thing is, point 5, does A equal alpha times R? That's how the problem is solved. All right. We didn't get quite as far as I wanted. We did okay. I will see you all tomorrow, and hopefully tomorrow night. Actually, I will not be in class tomorrow, but I hope to see you all tomorrow night.